So everybody welcome back to this channel, and for today's episode we are going to study a whole book, meteorology today. And I didn't mean to say that we'll be completing this whole book, but I meant to say that we'll be reading some pages of this book. We'll be learning about the meteorology, we'll be learning about the atmospheric science. So guys, if you are new to this channel, don't forget to hit the subscribe button right below. And for all others, like you want to study together, in this corona we are all alone, and we'll be needing each of us so that we learn better. So we can study together. Okay, you can play a song in the background. Actually, I have been playing, but I have actually not captured this because there will be a copyright issue. So stay tuned to this video and read more and more, because reading is cool, fun, amazing, fascinating. So guys, we are finally to this page 6, chapter 1, a breath of fresh air. So well, I think the main book starts from right at this point. We'll continue reading more and more about this one. Stay tuned to this video. I think I'm disturbing you, be speaking in the middle, and I'll be speaking for some long time after this video. Okay. So if you are wondering what I'm actually writing, I'm writing quite vocabularies. There are some words I frequently or I never use, but they're in this book, and when I see these words, I like to use them in, which means that my English will improve. I hope that I just hope. I don't know it's going to improve or not, but I hope. One breath of air is equal to 10 to the power 22 molecules. Wow, almost close to, not close, but 10 to the power 23 is 1 mole, right? 6.023 into 10 to the power 23 is 1 mole. And you see, look, in one breath of air, how much? 10 to the power 22 molecules. That's incredible. Life is fascinating. Earth is fascinating. Everything in Earth is fascinating, by the way. I have to take note of these important points, okay? And that's what I'm writing right now. Wow, that's incredible, guys. 10 to the power 22 stars in the universe. You see, like I have to read this again. I didn't understand that. How large this number is when you compare to the number of stars in the universe. Astronomers estimated that there are about 100 billion stars in just 100, which means 10 to the power 11. Okay, stars in average size galaxy, and there may be as many as 10 to the power 11 galaxies in the universe. To determine the total number of stars in the galaxy, you multiply the number of stars in the galaxy by the total number of galaxies and obtain 10 to the power 11. Okay, that's incredible, guys. The number of molecules that gets inside our mouth at one time is so large. That there are that many stars. That many stars we are inhaling actually. Consider that one. We are inhaling 10 to the power 20 stars at a time. Considering the stars to be electrons, protons, therefore, each breath of air contains about as many molecules as three. There are stars in the known universe. Incredible, guys! Fascinating. I love this book. This is the reason that I love this kind of book. Okay, in the entire atmosphere, there are nearly 10 to the power 44 molecules. It might seem like 10 to the power 22 and 10 to the power 23 to be a close number, but that's really incredible. Like I said, okay, they may be close. A bit of some minutes ago, I said that 10 to the power 22 and 10 to the power 23 were somehow close, but they are not. Look at this. There's another incredible line in this book. Therefore, each breath of air contains about as many molecules as there are stars in the known universe. Yes, obviously. In the entire atmosphere, there are nearly 10 to the power 44 molecules. Entire universe 10 to the power 44 molecules. Now it might sound like we breathe 10 to the power 22 molecules at a time, but there are altogether 10 to the power 44 molecules in the universe. Isn't that sounding a bit of weenie or something confusing? No, it isn't, but 10 to the power 44 is very, very large number. Do you know the mass of a mass of a photon? 10 to the power minus 51 kg. I think that's probably kg. And you see 10 to the power 45 is incredible number, okay? 10 to the power 20 constantly. Wow. Water vapor is an extremely important gas in our atmosphere. Not only does it form into solid, both liquid and solid cloud particles that grow in size and fall to earth as precipitations, but it also releases large amount of heat, called latent heat. When it changes from vapor into liquid, water, and ice, latent heat is an important source of atmospheric energy, especially for storms such as thunderstorms and hurricanes. But how? Let me see. Moreover, water vapor is a potent greenhouse gas because it strongly absorbs a portion of Earth's outgoing radiant energy, somewhat like the glass of a greenhouse prevents the heat inside from escaping and mixing with the outside air. This trapping of heat energy close to the Earth's surface, called the greenhouse effect, keeps the average air temperature near the surface much warmer than it will be otherwise. Thus, water vapor plays a significant role in the Earth's heat energy balance. Okay, I understood that water vapor is also a greenhouse gas. It also traps the heat. Okay, I had known that before as well. But what I'm not getting is that the use of the latent heat in the thunderstorms. I don't know. Let me see. Okay, what is happening here? What way? Origin extra. Okay, I understand. One. Okay. Maybe we'll try to find the answers a bit later. But I think what to assume. Okay. Now there's a latent heat in the atmosphere. When the water is in a gas form in the atmosphere, that changes into the liquid, and in that process, it's just going to remove out the heat, and that heat will be used by the hurricanes and thunderstorms. I think that is what this book is trying to say, by the way. So probably that is what we should never be sure. Okay, guys. First of all, one thing I want to say is that never believe in YouTuber alone. Okay, they do the research, but they do research. Yes, I understand, but you should never believe in them. You should try to do your own research. I suggest you, yes. Even though I'm also kind of a small, very, very small, tiny YouTuber, I know, how YouTube works. I've been trying to do YouTube for almost 2 years, and finally I've started like this. And I don't know that if it's going to be good or not, but I think it will be because I'm trying my best. Carbon dioxide and natural component of the atmosphere are very small. Yeah, 0.03 percentage. And sometimes, like some books also mention it's 0.04, and don't get confused. 0.039 is almost exact, and now rounding that off, it becomes 0.04. Okay, so some people might say, okay, that carbon content in the atmosphere, in Earth's atmosphere, is only 0.03, and someone might say 0.04. In this sense, we have to say that the one who says 0.04 is more correct one, because the exact is 0.039. So rounding that off, zero point 0.4 is much closer than zero point 0.3, right? Carbon dioxide enters the atmosphere mainly from the decay of vegetations, but it also comes from the volcanic eruptions, the exhalations of animals' life, from the burning of fossil fuels, and from deforestation. Okay, deforestation. How does that come into the atmosphere? You cut the tree, how does that is going to contribute the carbon in the environment? Maybe the trees which absorb the carbon dioxide to prepare food, maybe they die out, and because of that, the larger amount of the carbon dioxide gets or remain in the atmosphere. I think that is what this book is trying to say. Okay, I'm done up to this part, and now I'll start from how much. Okay, the removal of carbon dioxide from the atmosphere uh, takes place now. It Look at this. Okay, now I just read this part. Now this is the next page, and I should not start from this one. Okay, this one. Now I have to go from this side. Now where is the nearest point of this side? Okay, this one here. Okay, I have to start reading from here. I have to go up to this place, and when this page ends right here, okay, now I have to go here. This is how you have to do. Don't just read. Okay, now you ended up your place, and now you start. If you start reading about books from right at this part, then you are actually doing mistake. Okay, so I was here saying the removal of carbon dioxide from the atmosphere takes place during photosynthesis, as plants consume carbon dioxide to produce green matter. Not only the green matter, okay, the plants use carbon dioxide to prepare the food, and from the food they get energy. Energy is absorbed from the sugars they produce. That's how the carbon gets absorbed. The carbon dioxide is then stored in roots, branches, and leaves. The oceans act as a huge reservoir of the carbon dioxide. As phytoplanktons, phytoplanktons, the lowermost in the tropic level, very tiny organisms, tiny drifting plants. In surface water, fix carbon dioxide into organic tissues. Carbon dioxide that dissolves directly into surface water mixes downward and circulates through greater depths. Estimates are that ocean holds more than 50 times the total atmospheric carbon dioxide content. Look at this. What these estimates are that ocean holds more than 50 times the total atmospheric carbon dioxide content. Oh yes, and I also want to add one small thing here. So when we talk about global warming, we are talking about ocean warming. Okay, only few percentage of the carbon that is being added to the environment in today's century is actually being added to the air, and a maximum portions of that carbon dioxide is being added to the ocean, and because of that our coral reefs are dying, our oceans is increasing its volume, and the biodiversity in the oceans is decreasing, alpha diversity is getting really low due to different ocean uh, area. Okay, so where I was, yes, here they store more than 50 times more. 50 times is so much, guys. Just imagine how much is the 50 times. Figure 1.5 reveals, okay, what is a figure 1.5? This is, look at this, figure 1.3, okay, figure 1.4, and figure 1.5 should be somewhere here. Okay, this, look at this figure. We see the atmospheric carbon dioxide concentration in 1960. This it was just 315, and now by 2010 it has, skyrocketed to almost, I don't know how much it is, 390 parts per million. That's really huge, leap, and that's a really bad leap. Reveals that atmospheric concentration of carbon dioxide risen about reveals that atmospheric concentration of carbon dioxide risen by about 20% since 1958, when it was first measured at Mauna Loa Observatory in Hawaii. This increase means that carbon dioxide is entering the atmosphere at a greater rate than it is being removed. Yes, sir. The increase appears to be due mainly to the burning fossils of fossil fuels. However, deforestation also plays a role, as a cut timber, burned or left to rot, release carbon dioxide directly into the air, perhaps accounting for about 20% of the observed increase. Measurements of carbon dioxide also comes from ice cores. Yes, and look at this. We geologists use the, the big taller coral reefs, tree rings, ice cores to measure the ages of the earth. Okay, what kind of atmosphere was in the earth in the back then. Okay, they use these three different kind. When I first learned that, okay, they also use the corals for that one, I was almost shocked, how do they do that? And then I see that corals behave in the similar way as the tree rings. Okay, they both have the rings like structures, and when there is higher temperature, the ring is a bit thick. When the temperature is lower, the ring is low, which means that if there is a thick ring, then at that particular point the temperature was higher in the atmosphere. That is what the geologists deduce from this, from studying these ice cores and corals. Okay, yes, now I just read that, okay, there's a 25% more carbon added every time. Okay, and that's based on the Mauna Loa observatory in Hawaii. Okay, the increase appears due to mainly the, okay, read that one. Now in Greenland and Antarctica, the Greenland and Antarctica, both of them lies in the northern hemisphere. Northern hemisphere, the part that lies further north of the equator. For example, tiny bubbles of air trapped within the ice. Okay, look at this. For example, tiny bubbles of air trapped within the ice sheets reveal that before the Industrial Revolution, carbon dioxide levels were stable at about 200 parts per million. Also, ppm can also be said as a milligrams per liter. Okay, don't get confused. Milligrams per liter and parts per million are same. Since the early 1900s, however, carbon dioxide levels have increased more than 40%, with carbon dioxide level presently increasing by about 0.4% annually. That's very bad, guys. You don't know the bad effects of the carbon dioxide in the atmosphere. When there used to be a lots of carbon dioxide in the atmosphere in the past, there were no lives, and now if we are heading towards that, and maybe probably the Earth will again be without life in the future. I'm not talking about just after 10 years or 20 years. I'm talking about our future means that it can be like 500 years after, 1000 years after. We have to see that in that way. Okay, not just after a decade. Now, okay, 0.4% annually. I did a mistake. Now I did it here. Now there's another row I have to go here. Okay, here 1.9 parts per million year. Scientists now estimate that the concentrations of carbon dioxide will likely rise from its current value of about 395 parts per million to value exceeding 500 by the end of the century. By the end of this century, guys, we are already close to 400 parts per million. That's going to be too dangerous, not only for the uh, environment, but also to the human. What will you do if we don't get fish from the ocean? Tell me, what will you do? Okay, what happened to the people who live in these equatorial areas in the low sea level, in the low altitude? The increased in sea level will obviously make them homeless, and these are really bad news. We all, especially scientists, like they are already concerned about this one. But as long as we have a dirty politics, I don't know how we are going to cope with this problem in the future. In terms of portions of the Earth's outgoing inertia. Consequently, with everything else being equal as the atmosphere concerned this global surface. In fact, over the last 100 years or so, the Earth's average surface temperature has warmed by more than 0.8 degrees Celsius. Okay, last. This is the thing, something. This is something that we should take note of. 100 degrees Celsius. Okay, 100 years and how much? How much temperature increase? 0.8. So, guys, don't get misguided at this particular point. Okay, 0.8 is the average increase. Okay, So just see that that's the average between extreme and the environment. It means that what happens to the extreme temperature. Maybe the Antarctic, which is to have just minus 30, might be getting minus 40 degrees Celsius. That's a 10-degree change, right? 0.8 is the average, considering both the cold and the hot, okay? It's just the average. Just think about the extreme change in the temperature, and that's the main part. Okay, what will organisms do? They won't be able to accommodate with these extreme temperatures, by the way. 0.8 degrees Celsius. Mathematical climate models that predict future atmospheric conditions estimate that if increasing level of carbon dioxide continue to at their present rates, the Earth's surface could warm by an additional 3 degrees Celsius. Oh, guys, by the end of this century, I think we are going to face all the calamities. You know how much is 3 degree Celsius change? Like we have a, okay, let's see from human's perspective. Okay, what is our average human temperature? 97.5 degree Fahrenheit, right? So if we just get like 100 degree Fahrenheit, we have extreme fever, we feel so sick, we can't do anything. And just imagine now 3 degree, almost 5 degree Fahrenheit change, and that's going to bring catastrophe. Okay, that's going to bring the geostorm in the earth. You understand what geostorm is? The series of this environmental catastrophes, hurricanes, volcanoes, earthquakes, all of these things together. Just imagine the geostorm. I'm not concerned about, okay, that these organisms will die. I'm not concerned about that other things will happen. I'm concerned that, okay, the only Earth that is in this whole universe is going to die, and that's because of the most intelligent people of this universe. A bit of responsibility is to everyone, okay, everyone. Just be a bit knowledgeous on this part. So we are here, okay, that's 0.8 degree Celsius increase by the within this 100 century. Okay, now within end of this century, we will have 3 degrees Celsius if we do not reduce our carbon emissions or greenhouse gas emissions. Okay, and now carbon dioxide and water vapor are not the only greenhouse gases, yes. Uh, Other includes methane, nitrous oxide, chlorofluorocarbons. Level of methane, for example, have been rising over the past century, increasing recently by about 1.5% per year. Most methane appears to derive from the breakdown of the plants and materials by certain bacteria in rice paddies. Wait, oxygen. Oh, look at this. Most methane appears to derive from the breakdown of the plant materials by certain bacteria in rice paddies. Wait, oxygen, poor soil, the biological activities of termites, and biochemical reactions in the stomachs of cows. So even if you burp, okay, that's going to release out the carbon dioxide into the atmosphere. So guys, be aware when you burp next time, okay? So this is what it's saying, okay? Even cows, they chew these green gases and they're going to burp out this carbon dioxide from them. Just why, not only carbon dioxide, also methane, okay? So methane is a major part over here. Just why methane should be increasing so rapidly is currently under study. Levels of nitrous oxide, commonly known as laughing gas, have been rising annually at the rate of about. So now I ended here, okay? Now I have to go down. Okay, there's nothing else. It means I have to go to the next page and I have to start from left side. 1/4 of a percent. We're talking about what? 1/4 of a percent. It means 25%. The use of the laughing gas is being used increased by 25%. Nitrous oxide forms in the soils through a chemical process involving bacteria and certain microbes. Ultraviolet light from sun destroys it. Chlorofluorocarbons represent a group of greenhouse gases that, up until the mid-1990s, had been increasing in concentration. At one time, there were most widely used propellants in spray cans. Today, however, they are mainly used as refrigerants, as propellants for the blowing of plastic foam insulations, and as solvents for cleaning electronic microcircuits. Although their average concentration in a volume of air is quite small, they have an important effect on our atmosphere. They not only have the potential for raising global temperature, they also part in destroying the gas ozone in the stratosphere, a region in the atmosphere located between 11 kilometer and 50 kilometer above the Earth's surface. We all know about the stratosphere, okay? We all know this one. I don't think I have to describe about that one. But if you are someone who don't know about the stratosphere, it's just a layer made up of ozone and that protects Earth from the ultraviolet rays. How does it protect? It's going to trap these ultraviolet rays and going to re-emit back to the atmosphere. That's the important part of this ozone, and they are the lifesaver. They are the blanket of the Earth's life. Okay. At the surface, ozone is the primary ingredient of photochemical smog. So guys, I think we will have to end right here. I think the video is already too long and I don't know if you are already bored.